Okay, we have one more speaker in this session left, and it will be Carlos Serrano from Lawrence Berkeley National Laboratory. Carlos is the Berkeley lead for the LCLS-II low-level RF project. His work focuses on FPGA and software design, mainly targeted to accelerator projects. For past few years, he has been working on LCLS-II, which is a 4 GeV superconducting LINAC currently under construction at SLAC to upgrade the existing FEL facilities.
Thank you. Good morning. I'm going to be talking about something we call the Cryomodule-on-Chip simulation engine, or CMOC, and several people were involved in this effort, and this is in the context of the LCLS-II project, which is a collaboration of several Department of Energy labs. So I'll talk about why we do this at all, and show some details about the physics, which is really at the core of this work, and then talk about the implementation inside an FPGA, and then I'll tell you what to think about this talk. So this was done for the in the design process of the low-level RF system for LCLS-II. And LCLS-II is an upgrade of the existing LCLS X-ray FEL at SLAC with a 4 GeV superconducting LINAC operating in CW mode with 1.3 gigahertz cavities. And here's a diagram showing the several feedback loops involved. And I want to point out that we're focusing on the RF loop here, controlling these cavities inside the cryomodules, and there is also beam-based feedback that is initially going to be implemented in EPICS to feedback on measurements on the beam itself. So here's a diagram of the low-level RF system. We use what we call a network-attached device approach, which is basically this chassis without these crates or micro TCA crates or VME or anything like that. They're just interconnected through fibers over the network. So the importance here is that the design is based on the importance of maximizing for channel-to-channel isolation, especially for the cavity signals the measurement of the cavity signals with respect to the signal that drives them. So what we did is separate the sensor from the feedback algorithm implementation into separate chassis, and they're interconnected through fibers, so they're opto-isolated. We get better than 90 dB channel-to-channel isolation within one chassis, and better than 120 dB channel-to-channel isolation between two channels on different chassis. So that's the main focus of this design. So before starting the engineering of a low-level RF project, you need to understand what you're doing. So we do this through simulation. First, we start with analytical study, which is basically determining the basic feedback equations, and then applying basic control theory to analyze stability. So this is where you get all the transfer functions and look for phase margins, and then out of these you get some information about the different trade-offs of the configuration of your feedback loops with your gains, and taking into account latency and everything else. And then we discretize those feedback equations, and then we run numerical simulations, first with software, so that we can look at the behavior of the system and start looking at plots and understand how the feedback system is working. And then we take this one step further, which is actually the main topic of this talk, which is to implement the same state space models that we do in software, but inside the FPGA itself. So basically, the final result is really a controller that is implemented inside this FPGA, and then the idea is to put in the rest of the system so that you have a closed feedback loop inside the FPGA, and then run the simulations to exercise the HDL implementation of this controller. So some details about the physics. Here's a picture of a 9-cell 1.3 gigahertz cavity, like the ones we were using. So the electrical properties of these cavities depends on its shape. So what's interesting here is that when you're feeling the field inside the cavity, it expands through the Lorentz forces, and then the resonance frequency shifts it decreases. So what we're doing is trying to stabilize this field inside the cavity, and then as you fill it up, then the electrical properties of the structure are changing. So in our models, we need to take this into account, and what we do is we take this 9-cell cavity and we decompose the field inside it into its eigenmodes, and then we apply the principle of superposition to calculate the overall field, and then each one of these boxes here represents each one of those eigenmodes, which is interesting in particular in these cavities because we have the fundamental mode that we want to excite to accelerate the beam, and then we have the 8π/9 mode that is very close to the fundamental, so we need to apply notch filter to notch it out inside the FPGA controller. So it's of particular interest for us to characterize these things. And then you have these boxes, each one for each mode, with different couplings to the high power amplifier source and to the beam, and then different couplings also to the probe, to the antenna that is measuring this field. And then you have these little boxes here that are labeled low pass filter at the resonance frequency of the mode, and that's the implementation of the response of each single eigenmode, which responds to the classic representation by an RLC parallel circuit. And here I show the first order differential equation governing the energy stored in this eigenmode at baseband. So then you take this superconducting cavity and then you soak it into this helium bath to cool it down to 2 Kelvin and then get these magical superconducting properties. And what happens there is that I was explaining earlier that with filling the cavity up with the field changes its shape, so it expands. And when you put it into this helium bath, then what happens is that these cavities, they start being interconnected through the mechanical structure, so through the helium bath itself and then the mechanical structure of the Cryomodule. So what happens is that as you fill up a cavity or change the field inside one cavity, it changes its shape and it's coupled through the mechanical resonances inside so it excites these mechanical resonances in these structures, and then it starts talking to the other cavities, and then those other cavities in turn have their electrical properties change. So this is a coupled system. So what we did to represent it, and these are important effects that you need to represent in order to have a proper model of your system and how the thing is behaving. So what we do is each one of these boxes represents this one 9-cell cavity with its feedback loop, the same way I was showing earlier, and then we add this box to represent the mechanical resonances inside the structure, and then here there's these electromechanical couplings that I was just explaining, so that you can have one cavity have its fill up, and then excite these mechanical resonances and then couple to the other cavities. And this is an effect that you can see in real superconducting cavities. So this is how it's shown, it's represented mathematically. We have the different, the energy stored in these different eigenmodes for each cavity, and then they exert a force that is proportional to the square root of the voltage. And then there is a coupling matrix, and then those forces excite the mechanical resonances, and we use a second order low pass filter, a textbook response for these resonances, for these eigenmodes, and then there's a displacement that gets created, and then those displacements are coupled to each cavity, and then there's this effect that it shifts the resonance frequency of each eigenmode. So we have these electromechanical interactions that are represented in this way. So how did we implement this? So I just talked about the physics. Then the way we did this is implement these models, and then I didn't show any equations today, but the paper has the full mathematical development in it. So these state space equations are coded into this FPGA. along with the real controller that is going to be implemented into to control the real cavities. And then there's a software driver that communicates with the FPGA to send control registers to set parameters, configuration parameters, and then there's live data that is coming back to the software. Then there is a conversion. Then, well, here on the top level, there is the user interface where the user is interacting with the model through setting some parameters in SI units. And then there's a middle layer that performs this translation between SI units and register values. Here is the diagram of the physics model representation inside the FPGA. We have the electromagnetic, well, this is the cavity electromagnetic simulator with the implementation of the electromagnetic Eigenmode response, the first order low-pass filter that I was showing earlier. And then here we have the mechanical resonances. And then here are the couplings from electromagnetic Eigenmode to mechanical mode. And then all of those, and then there is the displacements that are then propagated to the different modes to shift the resonance frequency. So it's just the HDL implementation of the diagram that I was showing earlier. And this is the controller. We convert to, there's a special care that you need to take into it's not the traditional PI loop in IQ representation for low-level RF systems, but you have to convert into amplitude and phase in order to satisfy this tune-up process, because when you're ramping up the field, then you're shifting the frequency and you need to control amplitude and phase independently. And this is a screenshot of the user interface showing cavity fields and things that you would see in a real cavity. And then there is a demo. I'll be doing a demo on Thursday's Speaker's Corner where I have a poster about the overall project. I'll be showing this running live in the FPGA. So the whole point is to get one step closer to the final result, which is the FPGA implementation of this controller. So running these simulations inside the FPGA allow us to not see the software representations of what we're trying to implement, but to see the actual thing working. It provides a tool so that you can have live simulations. You get waveforms getting to the user at the same rate as the real cavity. So there's this level of interaction, and you can look at longer timescales because this thing is running fast. And we can also test other things like the communications with the control systems and everything else. And one comment about open source, because of the talks earlier. We're in the process, we're a DOE lab, and I share Michael's concern about trying to basically make money of the inventions. And this design is being reviewed by our patent attorney so that we can release it to the public. And we have one advantage, because we're very good at convincing them that our ideas are worthless. So thank you.
Okay, are there any questions for Carlos?
I have one question, maybe two, depending on the answer to the first. If I understood well, you use a FPGA to embed a model, a physical model inside, right? But afterwards you control, the real controls doesn't take this into account. It's just for testing, right? Validation of the controls.
Controls, you're talking about feedback controls or control system?
Feedback controls.
So
you have your model in one chip, in one FPGA, and your control in another one.
No, it's in the same FPGA.
And when you work normally, you don't use this model. You know a normal control. You don't use model-based control.
No. So then we have a switch that can take either the simulated signals or the ones coming from the real ADCs.
Because if it's just for validation, in automation world, we used to do this thing offline. So I was wondering why you would complicate your life making an FPGA, sorry about that, when you can put all these equations with the physical meaning in an external tool which is meant for. And
there's a slight detail that when we were developing this, the cryomodules didn't exist. So this is a way for us to model, and also we're working at Berkeley and doing a lot of the digital design, and we don't have the access to superconducting cavities there. So a lot of the development happened before even the cryomodules existed. So that's the whole point of us getting there, and then we have a very high chance of the controller actually working. And it was fun.
Thank you.
Hello. About your model, how have you validated the model if you don't have real data yet?
These are well-known physics. We do have real data now, and the model is behaving, and we have experience running superconducting cavities. We haven't done and this is well-known in the literature. It's not something that we're inventing, and then nobody has represented this before. I have to say that we have done a lot of this work for qualitative sort of like functional checking, and we haven't yet, because we are just getting the first prototypes and the first production units. We're very busy working on to actually make it work, but we do count on making straight validations of taking the real data and then matching the models.
Okay, thank you.